So without further ado, I would like to welcome our presenter, who is currently in Greece, Professor Ioannis Zoufras, who is at the Athens University of Economics and Business at the Department of Statistics. Currently, he's the head of the school, and he's a well-known Bayesian statistician. And although I'm Greek, I don't know him personally before I sent him the invitation, but I knew his book about wingbacks and Bayesian statistics. And I thought that it would be a nice opportunity now that things can be done in Zoom to ask him for a presentation. So thank you very much, Ioanni. And before I hand over to you, since I'm based on Brisbane, I will, assuming I can find it, we will acknowledge the traditional owners as it's the custom in Australia and we require. I acknowledge the Turrbal and Yagara as the First Nations owners of the lands where QUT now stands. We pay respect to the elders, laws, customs, and creation spirits. We recognize that these lands have always been places of teaching, research, and learning. QUT acknowledges the important role Aboriginal and Torres Strait Islander people play within the community. And I will hand over to Ioannis. We will have 45 minutes of a presentation, or that's the plan, and then questions. Thank you very much, Kenny.
Thank you very much, Dimitris. Here in Athens, the weather is sunny, 15 degrees, a little bit chill for the Greek Athenian standards. As Dimitris said, my base is in Athens University of Economics, where I serve as a professor, and currently I'm the head of the department. And today I'm going to talk about volleyball and how we can use statistics to model volleyball. And volleyball is a sport that possibly not a lot of people know. Is not so popular as football or basketball, which are the most popular sports in Greece, for example. But it has some challenges in terms of statistics. This is a joint work with Leonardo Egidi, a very good friend and collaborator from the University of Trieste, Italy. And I would like to thank you before starting my talk about inviting me for this presentation, personally Dimitris, and also your branch of the Statistical Society of Australia. So let me see what's going on. Okay, so this will be the structure of my presentation. I'm going to first say some introductory comments about volleyball and the characteristics of the game and what are the challenges here. And then I'm going to go to one by one the features of the game and why it is difficult to model it and how we are going to model it. The third part is the basic model, and I'm going to show you step by step how we have built the model in order to satisfy the satisfy the features of the game. And in the fourth part, we are going to examine some extensions of the model, and finally results and implementation on Italian data. Okay, so volleyball, as I said, is quite popular in Greece, but it's not so popular as basketball and football. It's quite popular among women and girls, especially beach volley. I guess you might have it also in Australia. My daughter's just started also doing volleyball in her school, and and beach volley in a school near our house. So because it's not like other sports, and why it's not like other sports? Because football and basketball, usually you have one response. You have the number of goals or the number of points that you want to model, and usually you measure this on the two competing teams. Volleyball is not like that. You have multiple outcomes, and this introduces game complexity, which is not obvious how to model it. And therefore, in the past, as you will see, there were not very serious attempts to model volleyball. most of the analysis, the empirical works, are based on simple regressions or simplified models. There are two serious attempts. One is from Ferrante and Fonseca in 2004, where they used Markov models to model the sequences of volleyball outcomes. And the other is the approach of Gabriel, which is the same period as us. But although he had used hierarchical Bayesian models, which is close to ours, it had some violating assumptions that we try to deal with, and I'm going to show you here how we have done that. So the main reason for not having so many decent research modeling approaches is the complexity of the games. And as I said, most of the games are one level, one stage, one response, points, goals, and that's it. And usually Poisson was a standard way to model goals, for example. Here we cannot do that. Why? Because we have multiple outcomes. We have two outcomes in volleyball, and this is the points, the number of points, and the number of sets. And this multiple outcome measurement response is quite typical in all net and goal games where volleyball belongs. And in this category of games, we have the racket sports, mainly tennis is most popular, and maybe badminton. There are other sports here less popular. And also volleyball and foot volley is the two representatives, more popular representative from the body-based net and goal games. So how did I ended up modeling volleyball data? Actually, this is due to this guy, Sotiris Drikos, who is a good friend and collaborator, and he was the past manager of the Greek national volleyball team and Olympiakos here in Greece. And he also holds a PhD in volleyball performance analysis. And he came to my office, first of all, because he wanted to learn more about statistics when he was doing his PhD. And he also came to my courses, data analysis and Bayesian analysis. And after that, we worked on many projects. He always comes to my office, or we go for lunch or for a coffee. When we say coffee in Greece, we mean a social event where we go and discuss. And occasionally we drink also coffee, slowly, not like the Italians in a fast lane. And he always comes with problems, interesting problems, data. And that's why we started working on this volleyball data. Until now, we have 3 papers published, 2 of them with Sotiris. Currently, we work on the 4th project with him, and in the future, we have another problem that we are going to deal. So this ended up with very nice problems, data, and applications. So returning back to volleyball, what are the main features of the game and how we measure that? First of all, we have the game winner, which announced when one of the 2 teams wins 3 sets first. And how we specify the set winner. The set winner is the team that wins 25 points first. We have also the tie break, which is when the 2 teams are very close and they are 2-2 on sets. Then the last is called tie break, and it's shorter. It's only 15 points instead of 25. I'm saying that because all these characteristics, we should incorporate them in our model in order to be accurate. Another characteristic which complicates a lot the application, the applicability of the approach, is that when we have a tie in the 24 points, so when the 2 teams are 24-24, they play until one of the 2 teams gets a margin of 2 points. So finally the set may end up in 30 points, 30-28, or in 32 points, 32-30, and the winning team needs at least 2 points of difference. This is one of the characteristics that makes the modeling difficult. So there is a natural hierarchy of points and sets, and actually the way we think in the game is that we have the points, and when a team arrives in 25 points with a 2 points of margin, or 2 points of margin after 25, then we have the set winner. So the points announce the set winner, which is a bottom top approach. From sets we go to from points we go to sets. And I'm saying that because in our modeling approach, in order to simplify things, we are going to go to the other way around, from the sets to the points. So here the responses are 2, and we have the number of sets, and the number of sets can take very specific values. They can take values from 1 to 3 for each team, and the possible outcomes in terms of sets is, as you can understand, 3-0, 3-1, 3-2, 1-0-3, 1-3, and 2-3. So we have 6 outcomes in total. And if you can search, you will see that we have another paper working only on sets, but which is the terminal aim and the outcome that finally specifies the winner. But if we focus on the sports with only 6 outcomes, we lose a lot of information. We limit our events, while the point events are much richful in terms of information of the ability of the teams. And so, yeah, you can understand, since we have these possible outcomes, the number of the total number of sets that can be played in a game are ranging from 3 to 5. And of course, the number of points, they will range from 0 to 25 for the winner, or 15 if we have a tie break, or a little bit higher if we have the tie. But for the losing team, it will be from 0 to 23, plus the extra points if we have a tie. So this whole thing is quite challenging in terms of statistical point of view, because we have several different parts of the game that are not, there is no obvious model or distribution that we can use. So what we try to do to model every characteristic at a time, and then accumulate this model. And this, of course, as we teach in our students, this is called model building. And this is quite characteristic here to show how we build the model based on the characteristics. So as I said, we have 2 responses, and the natural hierarchy is to go from points to sets, but this is very difficult to model here. Why? Because the usual distribution that we use for other sports is the Poisson distribution, and usually we have the successes of the 2 teams, of the 2 opponent teams, and we model it as either with a Poisson or extensions of Poisson, using bivariate Poisson models and extensions. But here we cannot do that. Why? Because the way we have these points are much different. Moreover, we have repeated measures of points. So for every game, we record 3 to 5 sets. So the observation, the row here, the study unit will be not the game, but the number of each set. So we have one response saying who won the set, and another response with the points of each team. But if you think closely, we cannot use the Poisson. Why? Because the randomness in the point level, it is not in both teams. Because once we know the winner who won the set, we know that the winning team will have 25 or 15 points, plus extra points if we have ties. So actually there is no randomness when we don't have a tie, or there is a small randomness coming from ties. That's it. So we know almost surely what will be the points of the winner. What we don't know, and it's a random variable here that we need to model, is the points of the losing team. Okay, so this is where we are going to focus. And this is why the inverse approach, going from sets to points, is much easier here to model and to use. So what we do here, we start by modeling the sets, and then given that we know who won the set, then we model the losing points. So the other characteristic that we need to embody, and we are going to do it in the second level because it's not obvious how to do it, is how we are going to incorporate the additional points due to the 2 points of margin needed in order to announce the winner of the set. And this is an extra characteristic. And finally, the characteristic of the tie break when we are in the 5th set, we do not terminate the level, the set in the 25 points, but on the 15 points. Actually, this final characteristic is not so difficult to incorporate in our modeling approach. So before I start, just one or two definitions and notation. We denote by YAS and YBS the points at the S set when two teams A and B are competing to each other, and the home team is the A team. So here, this will be the home team. And we use YS, which is just a binary indicator, which specifies which is the winner of the S set. Okay, so this will take the value of 1 when home wins and 0 otherwise. And then we combine this in order to get the points of the losing team, which will be the second outcome we are going to use. So when the home team wins, then the losing points are coming from the second team, from B team. And when the home team loses, then the losing points will come from this home team. This is the whole idea here. Have in mind that here we are going initially to go with the assumption that we do not have any extra points. So the points of the losing team should range from 0 to 24, or if you consider the 2-point margins, to 23. So the first level, the set level, is not very difficult to model. Actually, you can just consider a Bernoulli distribution and the logistic regression type of model. So this is quite easy to model. And the second level here is the most difficult. Here, to simplify, first, we assume that the opponent wins when we arrive at RS points, which will be 25 for the first 4 sets and 15 for the last set. Okay, so this will be the RS. So given that we know the winner, as I said, the points of the winner are known, given the assumption that we do not have any extra points, but the randomness comes from the points of the losing team at the set level. So what else we have here? The Poisson is not a good option. We could have used the truncated Poisson distribution, but it's much more natural to use the negative binomial distribution. Why? Because the negative binomial distribution describes the number of successes until we have RS failures, and here successes are the points of the losing team. And here, the failures, as we measure here, will be the points of the winning team. And as we said, this will be 25 or 15 here, making the assumption that we will not have extra points. I'm doing that in order to focus first on the first part and then introduce the extra points in the model. So we need something like a truncation here in order to consider that the number of points that the losing team will get will be truncated. It will not be higher than 25. And here we put RS minus 2 in order to incorporate also the 2 points of margin at this level. So the second level will have a negative binomial distribution. This will be the success probability for the losing team. And this will be the total number of points won by the opponent, 25 or 15, depending on the set level. And this is the restriction to make this lower than equal or lower than 23. Let's put some structure now to the parameters. So in the first level, as I said, it's simply a logistic regression model. And here we use this is the usual vanilla structure in sports, where we have a home parameter. This is the home effect in the set level. And these are the set abilities. Okay, so if the home effect in almost all sports is empirically proven with several studies. In football, there is much more discussion about the home level and how strong it is, and usually it is related how live are the spectators. So here we use the home effect. If the home effect is 0, then actually we expect that two teams of equal strength it will have 50% probability to win. It will be a game of actually of having 50% to win every set. Any positive here value, it will give some bonus, to the home team, and these are the so-called team abilities, and the team abilities and capture how efficient are the teams in the set level. So here we use also corner constraints, which means that every ability will be compared to the average level. Positive parameters, it will show teams that are better than average, and negative values will show teams that are worse than average. And again, here we use similar structure. Again, it's a type of logistic link, if you can think. But here we have introduced also the WS, and here I forgot a bracket, the WS, in order to account which team points we are modeling every time. So actually here, if we have the home team winning, then the home effect will be eliminated. This is a home effect at the points level. Is different than this one because the scale of the two measurements is different. And these are the abilities of the teams in the point level. Again, it shows how efficient is a team in winning points now, okay, which is a little bit different. It should be connected. These two are definitely connected, should be connected, but it's not exactly the same thing. So here, when the home team is winning, this will take the value of 1, and this will be eliminated. Why? Because we model the away team, which is the losing team here. And here we'll have a minus, which means that we'll take the ability of the away team minus the ability of the home team. And if the home team loses, then we model the home team points because it's the losing team, and this will be equal to 0. The home effect will be introduced in the linear predictor, and then the difference will be of the home team versus the away team. Okay, so this is how W controls which parameters, which points we model at every level. And here we need to complete the formulation. We need 2 extra equations, which are not very difficult to think. The first is the adjustment for the tie breaks. So what this equation says, when we are in the fifth set, then take 15 points instead of 25. And the last of the equation, it says that depending on W, consider here the observed points for this part to be taken either from the B points or the A points, depending on who won in the first level. We had a look on the expected points because, you know, when we model, usually we are interested in the expected number of points, and this is the expected points of the 2 teams when we know who won. Okay, so this is based on the negative binomial distribution without any restriction. And as you can see here is with the truncation. So when we introduce more and more complexity to our model, the equation becomes more and more difficult. In order to understand how it works, we did this graph. And here on the horizontal graph, we have the probability of the home team winning. And here is the expected points of the losing team, which are the 2 main measurements here, the parameters of the main parameters of the 2 teams. And you can see when, for example, the home team has a probability of winning very high, 80%, then the probability of the losing team is, the expected points of the losing team is about 7. And as this probability is getting lower, then the losing team will have higher expected points. And it says that even if a better team loses, then it will lose with a lot of points. The set will be very, very close in terms of points. And this is the final expectation of the 2 teams. Here we have introduced also the RS in the equation. As you can see, it's very complicated, but still we have a closed form expression for the expectation of points. So the next step is to go to the implementation. In the implementation, we have used the Bayesian approach with non-informative priors. We have here used sum to zero constraint for the abilities. I have already said that. We have done this for both the point and the point at the set level. We have used JAX in order to estimate the posterior distribution, and the data are coming from the Italian SuperLega. Before we proceed to the final results, we have something more to incorporate. We haven't done anything about the extra points, and this is a problem, as you will see later on. If we leave it like that, the model will not behave very well. So we have used an inflated model for the extra points. Actually, the extra points here are denoted by OS, and actually, if zeta s are the observed points, then this will be given. We know we can calculate in every game how many extra points we have by considering the zeta s of the winning team for the winning team minus RS, which is the points that they were expected to play if we didn't have extra points. So these are the observed points. Just 1 minute to erase this because. So these are the observed points, and the observed points of the teams will be equal to YS, and here I'm referring to the losing team plus the extra points. So these are the normal points that will be of the losing team that will be up to RS, and these are the extra points which are due to ties. And for this OS, we are going to use a zero inflated Poisson distribution, and the PS is the probability of having extra points, of playing extra points, and lambda will be the expected extra points. And the YS will follow a negative binomial distribution as usually. Actually here, this, as I said, these are the points of the losing team again. If we want to find the points of the winning team, it will be RS plus OS. Okay, but as I said, I'm not dealing with that in the model because we know this RS and OS will come to this equation, so we can estimate everything from here. This is the complete formulation for the second part, and I think with this we have addressed the most important issues in our model. The first evaluation, we have used DIC here to compare the models. The first evaluation, we have done 3 models. The first one I have used for the points just a Poisson distribution, the simplest possible. We discussed why Poisson is not the best model, but I have done that just for comparison. The second is the truncated by negative binomial, but without extra points. And as you can see here, the fact that I have not used extra points makes the truncated negative binomial worse. Why? Because there is a part in the model that I haven't modeled at all. An alternative here would have been to remove the extra points and model directly the truncated negative and use directly the truncated negative binomial on the actual points without the excess of points, but we haven't done that. We have done the full model here, which actually improves the DIC over the Poisson and of course over this model that ignores the extra points. So in the first, sorry, is there any question? No. So at the first step, we see that the model we have introduced here is indeed better than just doing something easy, and the extra points are needed to be incorporated in the model here. The second, here we are going to see also some extensions. The first is, as I said, the abilities of the sets. These are the set abilities, and these are the point abilities, should somehow be connected in the set level, because at the end, the team is determined by the sets won, not the points. So what we have done here, we have introduced the point ability difference as a covariate in the set level. And because we were not sure that both of these will be needed, we have used these indicators, V1 and N1, Nu1 and Nu2, in order to control, to take all possible combinations and see what we need here, what we need to introduce in this part of the analysis. When we have both parts, the point and the set abilities will act as an excess of ability in terms of winning the set at the set level. So if a team is more efficient in the set level than in the point level, then this will make the difference. If these abilities are enough to explain what's going on the set level, then this will not be introduced in the model. So these are the combinations. If both V's on U's are equal to 0, then we do not, the team abilities are not influencing the winning, the probability of winning a set, which is not realistic. Actually, it's like we're saying that everything is random. If we have the first indicator equal to 1 and the second equal to 0, we have the model we discussed until now, which are the separate abilities on the set and the point level. When we have this part, then this will be removed from the model, and all the modeling will be done by the ability of the teams, and the information will be carried out, will be moved from the two levels of the responses. And finally, when we have both of the abilities, as I said, this part will act like an excess of efficiency of the teams in terms of winning a set. Another thing that we have incorporated in the model is we have used some random effects on the point level to introduce the correlation, the possible correlation between the different sets. We have not seen very much improvement. If you see here, this is the standard deviation of the random effects, which is quite small. Is not much different. We'll see later that from the DIC here are the DICs, that it makes a small difference. Actually, the DICs are quite identical. It's a little bit better, but here we did not continue with these random effects, because this makes the model much more intense, and the difference in the prediction was small. The other thing that we do in sports is to consider dynamic abilities. What is dynamic abilities? The model that we have considered until now assumes that the ability of the teams, either in the point or the set level, is fixed and constant across the whole season. As we know, we have a feeling that the performance of the teams is not constant across the season. It has ups and downs, especially when the team is of lower level. So it's quite standard in sports to use this structure, which is simple, the abilities of every week or game to depend on the previous ability. This is a simple random walk or autoregressive one structure. And we have done this in the point level. You can see some variability, but it's not critical. Here, Ravenna has ups and downs, as you can see. The ups and the down is in the middle of the season, and at the beginning, at the end, they have much better performance. All the other teams they have some variability, but not very strong. If you see here, the sigma, the standard deviation of these dynamic effects is not very high. Actually, it's very small. And similar is the picture also on the set abilities. As we will see here, in the next tables, you will see that the effect was minimal. Before we continue, also we have in the model with having both the team and point abilities connected, we have done this graph, which is usually called also forest plot, with the posterior intervals of the abilities. Here you can see the abilities on the point level, and you can divide the teams in the teams above average, in the teams or being average, and these teams to be a little bit worse than average. When you go to the set level, which is, again, I remind you, this is the extra ability, the extra efficiency in the set level. You can see that all of them are very close to 0, very central. These two teams are making a small difference in the sense that a big part of the posterior is away from 0, not all of it, but this is Padova and Verona. And as we will see, this makes a difference in the model. So if you eliminate all the other things, my mobile is ringing. Everybody remind me now. If you eliminate all the other extra set abilities and leave these two, you can see again that this is at the margin of significance, and we are going to evaluate these models using DIC to be sure what's going on here. So if we see all these models here, this is the basic model, the truncated negative binomial with extra points. And if we see what happens if we introduce connected abilities, and this is connected abilities, and here we have only the point abilities in both levels, and here we have both on the point and set level. We can see that the point abilities in both levels is much better. It improves the whole picture of the model. And because we have observed this difference for Verona and Padova, we tried also to keep these two in the model. And if you see, this also makes a difference. So we decided to leave Verona and Padova inside as different set abilities. What does this mean about Verona and Padova? It means that in the set ability, they are even more efficient. So even if we in the point level, they lose more points than expected, they are not very efficient there. At the end, they may win or they may lose. They may win because they have positive abilities, the set, even if they are not so efficient in the point level. And this usually has to do also with the quality of the players. The last part that I want to discuss is what happens with the dynamic abilities. In the point level, the dynamic abilities do not seem to be important. The DIC's level. In the set level, it is a little bit better than the basic model. But if you go here in the model combining abilities, then this is better. So this is our final model that we are going to use. Finally, what we have done, we tried to model a little bit the probability to explore to see what happens with the probability of having extra points. What we intuitively expect here is that teams that are close in terms of abilities will have higher probability to play for extra points. And that's why initially we have introduced the linear effect of the point and set differences here. But then we realized that the effect is not on the actual difference, but on the absolute values. Why? Because when you have teams of equal strength, then we expect to have higher probability of playing extra points. And the difference doesn't, if it's positive or negative, the difference shouldn't play any difference in this probability. So here we replace this with a more general function of the differences. And we have tried several functions, simple linear effect, because this was our initially thought. Then we use the absolute differences here, quadratic relationship without absolute, and here we have introduced absolute. All these attempts were not successful. Everything we did, it did not improve the fit of the model. So we stayed with the basic model. Actually, what this implies is that the probability of extra points is a little bit random. It does not depend on how close are the teams, as our initially intuition was there. And this is the final table of our model. When I first saw it, I said it's a beauty. For many people outside our field, it will look like Chinese or Greek, but I thought it's a very nice model to summarize everything in this way. Let's see some results now based on the fit of the model and the prediction. Here we have the difference in terms of points. The white, the solid line is the observed differences, and the other blue lines here are the ones estimated by the predictive distribution. And here we have reproduced the tournament, the full season tournament, and we have calculated using the predictive distribution, and we have calculated the number of points based on the model. And here we present the expected number of points. So this is the posterior mean of the points and based on the predicted distribution. And here is the ranking. And as you can see, the ranking is based again on the posterior mean of the points. And you can see that here we have reproduced the league accurately. The only difference was here at the bottom. Have in mind that this is ensemble goodness of it, because we have used all data and we have fitted the model and we have reproduced the league using the posterior predicted distribution using this data. And here you can see also the confidence interval. So the model is quite accurate, and it was quite surprising when we saw that it went so well. And after discussion with Sotiris, who is, as I said, the expert, we reached the conclusion that volleyball is not a game with a lot of variability like football. Football is very difficult to model. Why? Because we have a small number of events, small information about the response, and the surprise is very easy. There is a lot of variability. In volleyball, because we have many successes and we have this hierarchical structure, usually the strongest team will win, and this is also reflected here in this simple model, because here we have used the simplest possible model, minimal information, just the teams, who is the home team, and actually nothing more. Maybe also the sequence of the games if we use dynamic structure. Here are out of sample predictions. We have done two scenarios. The two scenarios that are more interesting for the fans. The one is we took the data in the half season and we tried to estimate the rest of the season. This is quite critical for the fans, for the spectators in many sports. For example, in football in Greece, we announce an informal winner of the winter when we have the half of the season. And it's very nice also in terms of statistical perspective, because all the teams have played to each other, but not but only on the one home stadium, or only on one stadium. So we need to expect the rest of the season to also complete, to have a full balance design in terms of the tournament. So here, if you use the predictive distribution to see how well, how many games we predicted well, we have the posterior mean of about 78% of the games predicted accurately. And if we go to the playoffs are a little bit more difficult. Why? Because the teams are more determined there, and sometimes we have some surprises, especially when they play in the home ground of the weakest team. Usually they do their best and they try to win in order to continue the series of the games. And here here we have used the full season data in order to predict what happened in the playoffs. And you can see here that the posterior mean of the correct prediction is about 71%. So overall, I would say that we are satisfied with that. And here is a graph again, and we have the points. With blue is the posterior expected points, with black the observed points. This is the interval, the posterior interval. So everything is well predicted, with the exception of two teams. These two teams, Padova and Trentino, which are out of the intervals, but not so. This is I don't think that this is so critical for the overall conclusion. Again, here this is the out of sample prediction, not like the previous approach that we have done, the in sample prediction, and this is again another outcome. Here we have the probability of ranking for each team. With red is the observed one. So if you see one by one the teams, you'll see that in most teams we have predicted correctly the winner. There are some exceptions, not the winner, the correct ranking, sorry. We have some exceptions, for example, here, Verona here, and Padova here. All the rest of the teams are quite successful or quite close to the correct ranking. Again, this is at the mid-season scenario. Finally, here we have the playoffs results, the playoff results. Here the result is the number of games won by its team. So it's not exactly what we modeled. And here in brackets, in small letters, the posterior probability of winning. So here Tredino had 60-40%, and the games were quite close. Here we had Perugia sure winner, but it had some difficulties. Modena 76 probability won comfortably, and Civitanova also high probability and won comfortably. The same here. Perugia was the clear favorite, but won difficulty with a difficulty 3-2 in terms of games. Civitanova again was supposed to be a better team, 65 versus 35. Again, we had Civitanova predicted correctly, and finally Perugia won the trophy. The probability for this game for Perugia winning was 78%, and the probability of Perugia winning the tournament when we finished the full season was, according to the model, was 74%. And the Civitanova was the second best team according to the full season with 14% probability. This table shows the probabilities for each team to advance to the next round. For example, Perugia was, according to the model, was quite sure to go to the semifinals, 96 probability to go to the final, and 74-75 probability to be the winner of the tournament. Civitanova 87% to go to the semifinal, 58 to go to the final, and 14% to win the tournament. And the rest of the probability. So you can see that we had the clear two favorites for the final, and this was the final scenario also here. So to wrap up, we have introduced a unified model for volleyball. The proposed model accounts for all volleyball characteristics. It combines information for both sets and points, which is quite innovative here. The fit here, I believe it was quite impressive. So we had an excellent fit, and we had full regeneration of the league. The proposed model has good overall predictive ability. And for future work, we are working now to incorporate the importance of skills. There are several skills that are recorded in volleyball, and we would like to see what is the measure of these skills. And we can also build predictive models using covariates. I think this is of secondary importance because in the first approach, the models will be similar, but in the first level, we use the skills to understand the game, to understand what is the weakness or the strength of each team and each player, and to evaluate the overall performance. And this is much more important from the perspective of the manager, while prediction here in volleyball, because it's not so popular, is only interesting from the fans' perspective, and it is of secondary importance here. So time for coffee, evening coffee for you, morning coffee for me. Thank you very much for watching.
Thank you very much, Yanni. That was very interesting. Can I open the floor to questions? Any questions for Yannis? If so, please unmute your microphone and fire away. I was going to ask somebody else. Sotiri, you're here. I can see you. I was going to ask.
Yes, I'm here. But
so
my camera has a problem. Yeah, but I'm here.
Sotiri, you are the manager, if you like. I was going to ask you. This is a rare opportunity where we have somebody who is outside of statistics, let's say, or who has the problem. What was the usefulness of this for you? What did you learn from this big exercise? What was there something that you learned that you could use? That's my question, Sotiri.
Of course. Yes, okay.
Or for Yannis, but
I will say my opinion after.
Okay. I would like to say that this kind of approach is a little bit difficult, to follow by the experts of the sports, coaches or managers or technical directors. This kind of approach, but I believe that there is some other kind of approaches with lighter, I can say, version of statistics that it would be very useful to guide a team to select the proper players or to select the proper, tactical system of the game, and for each match, and for generally for a season. Because volleyball, like all the other professional sports, the teams used to change every summer. Every time we have a new team, that means it's a kind of casting. You have to select the proper players according to your budget, of course. Okay, and this kind of research is very useful for coaches, but not especially at this level of statistics, because it's not easy understandable for people of sports.
So will you say that when you go to the abilities modeling, as Yanis was saying, for the extensions, that will be something which will be more useful to you as a coach?
Of course, it is very important, to define which skills of the game at which time of the game are more important for success. And this kind of approach of our next work, I think it will be very useful, and according to the experts of the sports demands.
Yanni, what's your opinion?
Can I tell you how we worked in this model, and also in the other model that we have done, and Sotiris was participating on the set levels. We have introduced a model that models only the sets in another work. These are the basic models in order to build the second level analysis that it will be useful for managers. And in the second level, so we need to validate this model to say, okay, this model works, and it has a good predictive and good predictive ability and good fit, in order to be able to go to the second level, where we are going to introduce the skills and the important characteristics that managers use. And this is what we work now with Sotiris and Vasilis Palaskas, a student of mine who works in a sports company, and Leonardo. We use these two models in order to introduce the skills inside, quantify the contribution of each skill, and then we can measure what is the performance of each team at these skills, and then see what are the weaknesses of the team, and introduce new players, or see if a player is underperforming because a skill of him is not so strong, and so on. So this work was the basis to have a good model, and then add covariates that it will be important, and understand the game in the second level.
Basically, what you are saying is that you build a basic model which models very well the overall reality, and now you are going to refine it down so that you can add the player skills and expand it in that way. Another question I had was, why did you use the Italian volleyball league?
Italian volleyball, it is considered to be one of the best in Europe, and this was the main reason. So it's very central in the sport. Plus, my collaborator was Italian. In all the other papers, we have data from Greek championship due to Sotiris. Sotiris has very detailed data, and here we did not need a very detailed data because we're doing the basic modeling to see if everything is okay in the basic level. So
my question then, my follow-up question was, and I think you answered, the problem with you is that you answered all the questions that I noted, you answered them as you were going through, so yeah, you stole my questions. Anyway, I was going to ask if you have tried to validate or use this approach in other championships to see if...
No, we haven't done that. We haven't done that. My intention is to put an MSc student in the MSc level to take a lot of different championship and validate in many. Yeah. But my impression is it will be okay. It will be okay. This is my intuition.
Yeah. All right. Anyone else?
I don't know if Sotiris wants to add something about different championships because tournaments, because he has a better picture of the sport than me. So
okay, maybe it would be a good chance for us to study in championships from other continents, you know, because maybe sometimes Asian volleyball or North American volleyball is a little bit different than the European volleyball.
What about males and females? Do they have differences? Do you think?
Also, males and females are two totally different sports. With it's totally different sports. I believe maybe in other sports, but the male volleyball comparing to female volleyball, it's totally different in a lot of things. In the duration of the match, in the duration of the set, in the importance of the skills of the game. It's different, and I think it's a very big you know, area of research.
So when you say duration is connected with how close are the teams, because they play more points or not?
Oh, yes, it's not only how close are the teams, but it's the type of the game, because women are not so strong in attack. Attack is the skill that we take points more than any other scoring skill of volleyball, and this makes every rally in volleyball, in female volleyball, is a little bit bigger in duration than in teams volleyball, than in men's volleyball.
Okay.
Yeah, something that
you see like why I like talking with Sotiris. Every mathematical result has an interpretation from Sotiris, so I'm very satisfied with that.
Thank you, always.
if you throw something in new that you know, I would have thought that they are quite similar in the what you said about North America and European volleyball. For me, it would have been, yeah, same thing, different players. But you say that it's different, so
maybe it will be a little bit different, especially Asian volleyball with European volleyball.
Anyone else, instead of us Greeks dominating the discussion and me asking questions? Anything else, guys? Anyone has any questions? No. All right, then I would like to thank Ioannis for his very nice presentation, and it was a very nice model. And also I would like to thank Sotiris for giving a different perspective, the perspective of the user, if you like. Thank you very much, guys. Thank you very much, Ioannis, for doing this for us, and Sotiris for attending, and everyone else for turning up. Thank you, guys.
Thank you. Thank you very much.
See you the next. Yeah.
Thank you.
Have a lovely day.
Bye.
Bye.